Okay, to start off, we are going to graph this equation here, y equals 2x plus 1. All of you should know how to graph this. You look over to find the slope, which is 2 in this case, so you do rise over run, rise for 2 units, run for 1 unit, repeat, and connect the dots. So in this sense, slope is basically the rate of change, and whenever you see derivatives, always think rate of change, because that's exactly what derivatives are. When we find the derivative of 2x plus 1, the power of x decreases by 1, and we get y prime equals 2. When we graph that up here, we see a horizontal line, and this simply means that the rate of change of this graph is constant. All the points on y equals 2x plus 1 are increasing at a constant rate of 2. And what does dy over dx mean? That's easy. The change of y over the change of x, which is slope, which is derivatives. Alright, now we are going to graph y equals x minus 2 squared plus 4. Using this form of the quadratic equation, we can easily determine that the vertex of the parabola is at 2, 4. Then we can distribute to find the general form, which is y equals negative x squared plus 4x. We get negative 2x plus 4 for the derivative of the function. We can draw this line on our graph and plot some points. Now let's try to find the slope of the function at a point like 0, 0. We plug 0 into the x of our derivative expression and we get 4. This means that at 0, 0 the function is increasing at a rate of 4. As for the slope of the function at 3, 3, we plug in 3 for x and we get negative 2. This means that the function is decreasing at a rate of 2. Now let's take a closer look at the coordinates. For y equals negative x squared plus 4x, x1 equals 0, and y1 equals 0, and y prime equals 4, which is the slope that we found for the quadratic function at 0, 0. Similarly, when x equals 3, y equals 3, and y prime equals negative 2, which is also calculated the slope of the graph at that point. So to sum it up, at any x coordinate, y gives the vertical position of the point, and y prime, or the first derivative, gives the slope of the function at that x coordinate. Now let's talk derivatives in terms of physics, and let's start with position. When we talk about stationary objects, we're talking about objects whose positions are not changing. Hence, position can be used to describe an object's whereabouts. Velocity? Well, velocity is used to describe the rate at which position is changing in respect to time. I'm sure you've seen those speed limit signs by the road. What's the unit for the number? Miles per hour. So in essence, the unit for velocity is distance over time. Think of velocity as speed with direction. Hint, hint, velocity is a vector, so it has direction. And lastly, acceleration is the rate at which velocity changes in respect to time. If velocity either increases or decreases, we have acceleration. So we can say that the derivative of position is velocity, and the derivative of velocity is acceleration. So here we have a polar function, r equals 4, and we want to convert it to parametric equations using these two formulas. All we have to do is to substitute the r for 4, and there we got our parametric equations. That's easy. Well, it gets a bit harder when we are asked to find the position, velocity, and acceleration when t equals pi over 2 in terms of points or vectors. Let's start off with the easy one, position. We know position is all about location, so we're dealing with points here. We basically just plug pi over 2 in for t, and we get 0 for x and 4 for y. So position is at 0, 4. Velocity gets a bit complicated because we're now dealing with vectors, and we need to find the derivative of position functions. So derivative of cosine t is negative sine t, where we plug pi over 2 in for t and we get negative 4. And then for the y function, 4 sine t becomes 4 cosine t, where we get 0. Vectors have alligator jaws instead of parentheses. Acceleration. This time we are finding the derivatives of velocity. So the derivative of the x function is negative 4 cosine t, which gives us 0 for pi over 2, and the derivative of the y function is negative 4 sine t, which returns negative 4. This graph is a circle. Positions at the point 0, 4, then draw the vectors and don't forget the arrows. What's mind-blowing is that this graph actually simulates the orbit of Earth around the Sun. The velocity vector constantly changes the position of the Earth, while the acceleration vector, or the gravitational pull from the Sun, ensures a circular orbit.